Hello everyone, welcome back. Greetings from IIT Kanpur. So we were discussing about unit processes, and last discussion we saw about thin film processes. That's an overarching topic which covers all sorts of depositions. Today we'll talk one of the main ways in which we deposit thin films, which is the chemical vapor deposition process. So let's get started with that. So this particular topic I'll cover in two parts. So today we will be discussing about part 1. First, the disclaimer. This is the broad preamble about chemical vapor deposition in the context of VLSI processing. So I will have the following 5 sections in 2 lectures. Okay. In today's lecture, we will talk about the basics of CVD and CVD systems. In the next lecture, we will talk about the films that are deposited by CVD, especially amorphous and polycrystalline films. And then we will talk about refractive metal films by CVD briefly, and briefly about vapor phase epitaxy, which is increasingly important today in than modern devices. So let's get started with today's lecture. So first we'll talk about the basics of CVD. I've taken many of the ideas from chapter 6 of Wolf and Tauber book. This particular chapter was written by Andrew R. Colson and Richard Tauber, and you are welcome to refer to it as well for greater details. But the broad template I have used is that, and I have used some of the examples from there as well. So this is the outline about basics of CVD. I plan to touch upon 3 topics: talk about advantages and types of CVD, then what is the CVD process, what actually happens, a sequence of steps that are involved in that, and an understanding of that will help us also making sure that we get the films right. And then finally in this section I'll conclude with the regimes of operation based on what we know about how the CVD process happens. So just a quick recap. Thin films, we just touched upon this. What are the various properties that we are looking for in a thin film? First, of course, the process should be economical. I don't know whether to put it first or last, because if you decide that you want to have that process, often you find a way to make it economical. But all the same, the process should be economical in the sense that you should be able to scale it up, do large volumes of wafer processing with that, and overall cost should remain reasonable, so that the final cost is low. The thickness should be uniform. This is something that you want, especially when you have really thin films. If there is a variation of some fixed amount, say you are talking about nanometer thickness, tens of nanometer thickness, and you are finding tens of nanometer of variation, that's not good. So you have to make sure it's really high quality in terms of good thickness uniformity, high purity, and good density of the films. Many times there are trade-offs in this, but you want to make sure as far as possible high purity, electronic scale purity, and high density. Controlled composition and stoichiometries. So many times when you make thin films, the film stoichiometry is different from what you find in the bulk. Of course, that sometimes you do it consciously to get different properties, but many times that also weakens the property of that particular material. For example, silver is a very good conductor, but if it's not done properly, of course it's not stoichiometry there, but the film quality, there's a lot of porosity and so on, the conductivity will become poor. So we have to be careful on that. Similarly, SiO2 has some good properties, but if it's not stoichiometric, it moves away from the property that you want. High degree of structural perfection is needed wherever its crystalline nature, and also even some of the so-called amorphous material also we want some things that we can predict. SiO2, when we were discussing, we saw certain types of gaps that were there in the chains of the SiO2. They are not beneficial, whereas some are. So we have to make sure that we get proper structural perfection so that we can predict the properties of thin films, and it's useful for what we are doing it. Then of course the whole thing is for electronics, so we need good electrical properties and breakdown strength for a dielectric film, for example. So this is something that we have to make sure. And also increasingly important, especially with very fine dimensions and lithography requiring high planarity, and also you are sometimes stacking up devices, even chiplets on top of each other. You want very good planarity as much as possible, and that means that you should be able to predict how the deposition is taking place. Sometimes if there is a step, you want to kind of cover the step conformally. It should not be that there is a at that step corner it is very thin, or at the bottom of the top corner of the step you are having some thickness variation. So those could be the weak points, both from electrical property point of view, chemical property point of view. So we have to be very careful about that. So these are expectations of a thin film, and this is what we try to get from the chemical vapor deposition. So let us see what chemical vapor deposition offers us. Actually, we find that chemical vapor deposition can be done by various mechanisms. Okay, and why these various mechanisms? In fact, each of them tries to have some advantage. Maybe it brings down the cost, or maybe it makes the deposition conformal. Maybe you get very high purity or the predictable thickness. So depending on that, various CVD mechanisms have evolved. Of course, we won't be discussing all of it, but you should be aware that they exist. If you know the common ideas about CVD, you'll be able to easily pick up what is needed in the others. So quickly, to make sure that you are familiar with these, especially being a basic course, you should be familiar. Atmospheric pressure chemical vapor deposition. I'm not going to expand the chemical vapor deposition. I'll just call it CVD. That makes it convenient to say. Atmospheric pressure, CVD, APCVD. Then we have, when you have atmospheric pressure, you can always have low pressure, LPCVD. Then you have plasma enhanced chemical vapor deposition. We have touched upon these topics before. Then metal organic chemical vapor deposition. The Nobel Prize for last 2025 chemistry was for metal organic compounds. So this actually is very attractive in terms of sometimes lower temperature, sometimes high purity and simplicity of process, and so on. Then photon induced chemical vapor deposition. So photon, they have expanded the pH here and added, so pH CVD. Then ultra high vacuum CVD. Sometimes when you want to have some compound semiconductor growth and all that, you may want to go for ultra high vacuum chemical vapor deposition. Then you can have, this is a very interesting method of deposition. We will touch upon it very briefly in this lecture. Atomic layer deposition. So here this is becoming increasingly popular, especially when you want to have nano layers of various thin films. Then one of the lower cost methods is hot filament chemical vapor deposition. Some people even call it hot wire chemical vapor deposition, and so on. In fact, I'm sure there are many more that are going to come up over the years, and who knows, you may be involved in coming up with a new idea in the future. So we saw the requirements of thin films. We saw that a plethora of CVDs are available. But why is it preferred? So let me try to put some ideas where we can see why CVD might be more attractive. First of all, it's a chemical process. Selectivities can be good, and it can ensure that the purity of the films is very good. And especially some of the processes, you can ensure that. Atomic layer deposition, ALD for example, or ultra high vacuum chemical vapor deposition. And even normal CVDs that we talk about, LPCVD and PECVD, by proper design of the chamber and proper design of the process, you can get very good purities in this. The other interesting thing is, often the same chamber also can be used for depositing various chemicals, various layers. Even if there is a dedicated thing, the point that the whole idea can be replicated to deposit various types of films makes it very attractive. And the important point is, what CVD is able to achieve, often others are unable to achieve. So that itself makes it very attractive. It may not be something out of the world from the CVD point of view. It may be something very natural for CVD to do. For example, chemical reaction that is happening and you are able to deposit it on a surface at a very low cost. Maybe that whole idea itself is very chemical in nature, and chemical vapor deposition is more attractive. And also some of the newer ideas that have come up, clearly very difficult for any other process to emulate that. Finally, to the first order, CVD processes have been economically very reasonable, and the process control is very good. Even if initially there is some variation, by understanding the parameters, and especially with the advancement in technologies of pressure, temperature, and the flow rates and so on, and we'll talk about some of that a little bit today, you can actually make the process very robust and very reproducible even in a lab environment. So that's what is advantages about CVD. So we saw why CVD is advantageous and the types of CVD that is available. Okay, the very fact that there are so many of them means people have been thinking and trying to make that good. But then, what is the basic process of CVD? So let's try to view that in a very broad manner. Although there are many varieties of CVD, the basic idea is very similar. So if one may define it, the definition of CVD may be formulation of non-volatile solid film on substrate. Okay, first of all, it's forming thin film, that essentially, by reaction of vapor phase chemicals. This is where the CVD nature comes in. It's a reaction, chemical reaction of the vapor phase species that are brought in, and you want to do it in a particular way, and these vapor phase chemicals contain the constituents of the thin film which is going to be formed. So this is a very simple definition, and if you look at all the different CVDs, it sort of fits this. Okay, physical vapor deposition will not fit into this because there is no chemical reaction. You don't want chemical reaction, whereas here you want the chemical constituents to come, react, and just close to the surface it is forming the film. So you get fresh off the reaction, if I may say so, right? Just like fresh off the oven bread or fresh off the kitchen food. It's hot right there, very pure, and you are just putting it directly where you want. That is the whole idea. So that's the idea of CVD, chemical vapor deposition. So let's see how this happens. So first of all, as I mentioned, there should be some constituents that are coming in. So composition and flow of reactants and diluent gases. Diluent gases are essentially gases that are used to dilute the constituent reacting gases. Reacting gases, of course, by their very nature, it says they are reacting, but you want to make sure they don't just react in a random manner, in a controlled manner. So often you dilute it so that you can control the reaction rate. So we can express it schematically by this. Say there are two reactants, just for the sake of example, one blue and one green, and of course there are many of them. I have representative one, and then the diluent gases are also coming in. So they are coming in from somewhere. You make sure they are brought in, and then you make sure they come as close to the substrate as possible. Okay, so they are all coming here and they are moving in all various directions, and they are out here. Then following that, once you bring them close to the substrate, and we discussed this in the thin film also, the very nature of interaction, there will be a tendency for these molecules to come close to the substrate. Okay, and once they come to the close to the substrate, they get adsorbed, and hopefully they are chemisorbed. But as long as they are absorbed and they are moving on the surface, and that's the next step. Reactants are adsorbed to the surface substrate. Once they are adsorbed, they will move around, and if the temperature is appropriate, it may happen that these green and blue will react and form the product. I am just indicating by this, that depends on the stoichiometry and all that, the composition of the various compounds. A new compound is created, okay, and it is formed here. So that is indicated here. So the whole idea is gases are coming in from outside, you bring them, and preferably on the surface or very close to the surface, you want it to react and then form the product. The product is the constituent of the thin film, and then of course the constituents keep growing. Okay, and usually there is a byproduct that is also there. There's a byproduct that is formed, which I am showing by red. Red means we don't want that, right? when there is a reaction taking place, it's not that no byproducts they may be formed, but preferably we should, and not preferably, we should do our best to ensure that they are volatile or they are totally benign. If they are benign and they can be remaining there, maybe we can live with it, or it should just be volatile to just come out, and once they come out, they are removed out. Now the slowest rate step actually, so that you can see it's a sequence of steps 1, 2, 3, 4, 5, and it turns out the one that limits the speed at which you are able to grow the film is the one that is slowest, and you can sometimes artificially slow them or speed them up. For example, the amount of gases that are coming in, you can hold back, so you ensure that the reaction stops, right? Or you can increase the temperature of the substrate or lower the temperature. So those are ways in which you can control it. And of course, if the reactants are not removed, it may end up preventing further reactions from happening. Le Chatelier's principle, we remember, any reaction will move towards stopping its own things. So what you do, you have to remove the byproducts so that it doesn't prevent future reaction. So this is in a nutshell, what happens in a CVD process. And actually this is the desired process. So typically during the reaction, we saw that I mentioned here, substrate could be heated. You need energy for the reaction. Now this energy can come from heating. Then as we discussed, we can use plasma. The excited electrons in the plasma, they can end up activating or energizing the reactant species, and they end up reacting much better or at a lower temperature. Or it could be even photons that can come in and energize it. Okay. So there are photon induced chemical vapor deposition also is possible. So under presence of light, they react in the direction you want. Now this type of reaction that we discussed here, this is known as heterogeneous reaction. And heterogeneous, why? It is happening in the heterogeneous environment of the substrate or very close to the substrate. Okay. On the surface or just above the surface, the reaction is taking place and it's getting deposited. So it's not that it's getting reacted somewhere far up above and then it is the product is coming and absorbing and all that. You would prefer that the reaction takes place there. This is known as heterogeneous reaction. This is one of the ways it could happen. Of course, one can always say, why can't it react and fall? And of course, that's also a possibility. So that's known as a homogeneous reaction because it happens in the gas phase and you have the product, and the product comes and deposits as a thin film. So you have constituent gases coming in, and in the gas phase itself, the constituents are reacting and a product is formed, and a byproduct is also formed. So the product comes in then, and then that deposits on the surface, and then it will do whatever the thin film requirement is, that move on the surface, and gradually then it will form nucleation and so on, okay, coagulation and so on, and finally form the thin film. And then you have to pump away the byproducts, and the diluent gases will also be facilitating in that. As they are going away, they will also knock out the byproduct gases as they are going out. So this is in a way a summary of the basic CVD process. If you understand this, any of the CVD process we can classify into this category 1, 2, 3, 4, 5 and make sure that they are satisfied. In some, one of them is more critical, in another you maybe have better control of some of these processes, some you may not. So this is something that you have to do. That's where the variety of CVD process comes in. So note that the point I want to emphasize is, of course, there are various steps in sequence. Second, heterogeneous reaction happening right at the surface or just above the surface as it is absorbing, that would be the ideal. But then homogeneous reaction can also take place, and here remember that the reaction takes place in step 2 itself, whereas in the first one it takes place at step 3 or after step 3. Okay, so that's what it is. So now we have seen the basic process. Let's quickly compare the heterogeneous and homogeneous reaction. Okay, heterogeneous reaction, and it may be reiterating some of these points, but that's because that's the important aspect of the CVD that we want to keep in mind. Chemical reaction takes place in heterogeneous reaction very close to the substrate and as a phase reaction, right? Whereas homogeneous, it occurs in the gas phase. So it's so this is a heterogeneous phase, gas phase and solid phase, they are around there, and then the reactions taking place, whereas here it's happening purely in the gas phase. Now, what's the advantage of heterogeneous reaction? You can decide where the reaction will take place. Only where when the substrate is encountered, the reaction is going to take place. So, and actually you can control the process by heating or cooling the substrate. Of course, you can say you can heat and cool the volume of the thing, but that's more difficult. And sometimes even within the wafer, you may have some regions where you want more of the reaction to take place. So that they may be covered or not covered, and so those advantages are coming out in terms of heterogeneous reaction. So it occurs selectively over heated surfaces, and then it helps to form good quality films with much better adhesion. That is of course the biggest reason why we want to follow it, because as it is forming right there, there is no other interaction with any other molecule, and it is just interacting with the substrate, and the adhesion is usually better. So heterogeneous reaction is favored. What about homogeneous reaction? They form gas phase clusters. That's one risk that you run, because when it is reacting, they may come together and form clumps of the product. Many molecules may come together and deposit as a clump. That will prevent from getting good quality films. They can end up forming poor quality films, poor adhesion, because they are already adhered to each other, right? And low density and defects. Also, they end up consuming reactants and cause decrease in deposition rate. So they may end up not depositing the rate at which it's supposed to. You have less control. Essentially, that's the whole idea of the reaction. And as soon as it reacts, you want it to form in the film. So we saw that homogeneous and heterogeneous thing, and we would prefer heterogeneous, and that's what we strive for. Sometimes homogeneous happens, that also may be acceptable for certain processes, that we will have to accept it as it is. Now let us see the regimes of operation of the chemical vapor deposition. Clearly there are two parts to this, right? One is a gas phase part. Gas phase where the reactants are coming in and they have to diffuse to the substrate. The way you visualize it is there is a continuous stream of gas that is present. There is a boundary, and after that there is a region where there is a depletion of that gas as the reactant gases are going towards the substrate and reacting and getting depleted. Okay, so the gas phase reaction is the first one. This usually the gas phase reaction would be proportional to gas phase diffusion aspect of the CVD. Gas phase aspect of the CVD, the diffusion that takes place, that actually is dependent on temperature. Higher the temperature, faster it will be able to move. But actually it's a weaker function of the whole process of diffusion there in the gas phase is actually little weaker. It is temperature to the power 1.5 to 2. Okay, you have to determine empirically what it is for the particular system and how you have designed it. Then there is another thing that's involved in this, that is the reaction of rate, the reaction of the chemical reaction that is taking place. This reaction rate typically is Arrhenius relationship, R naught e to the power minus EA over KT. EA is some energy barrier that is to be overcome for the reaction to take place. T of course is absolute temperature, K is the Boltzmann constant. So now we can sort of divide the whole region of the space of deposition with temperature based on these concepts. So we can actually have y-axis, which tells the log it's a log scale. It talks about deposition rate in angstrom per minute or nanometer per minute, whichever. Angstrom per minute is more precise, right? So and remember that you want to grow it slowly because you are growing really thin films and you want to be able to control it. If it is angstrom per second, clearly you'll have less control than angstrom. So angstrom per minute, we usually use the minute thing, especially for certain types of deposition. So let's assume that that's a y-axis, and the x-axis is temperature. But notice it is a reciprocal temperature, 1 over T. Okay, so per Kelvin. So what does it mean? High temperature is to the left and low temperature is to the right, because when T is large, 1 over T is small, and you will find that here. And why are we doing this? That's because of the Arrhenius nature of the whole reaction that is taking place. So now when you look at it at low temperatures at this room temperature and around that, say here I have shown 1 over, this is schematic, there is nothing to be scaled here, 1 over 300 Kelvin or 1 over 600 Kelvin. So that's 300 around 330 degrees centigrade or something close to that. So in this these are temperatures that we have in the lab, which we can use for various processes. If you are using that thing and if you plot the rate at which the reaction is happening, it will go like that. It's a straight line because Arrhenius, and this is a log scale, right? So it will be a straight line. And what's the slope? Slope will give you the barrier that it has to overcome for the reaction to happen. Okay. Now this region is often called the reaction rate region. We'll see why in a short while. Then there is another regime. When we go to high temperatures, what ends up happening is whatever the reaction rate has gone up. Remember this Arrhenius relationship. So very high temperatures, the reaction rate goes to very high values. So when the reaction rate goes very high values, what may limit the rate at which the reaction will take place is how many species are coming to the reaction table, so to say, reaction region at that point. So very high temperatures, it will be limited by the diffusion rate of those species to where the reaction is taking place. At low temperature, what happens, since the reaction rate is low and diffusion usually in most of the systems is pretty high, and a lot of it can come to where the reaction is taking place. So there is no sparsity of species present for reaction to take place. What is limiting the reaction at low temperatures? What is limiting is the rate of reaction. At higher temperatures, what is limiting the reaction? How many species are able to come. Whatever comes, immediately they react, and then the whole system is waiting for more species to come for the reaction to take place. So you have two regimes, and this is actually limited by whatever is slower. So at high temperatures, we find that the reaction rate goes up very fast, and it's the transport that is limiting how much it is happening. And on the other hand, at low temperatures, and remember that this is to 1.5, so this will be a straight line with slope of 1.5 or 2 or something like that. So at low temperatures, the slower one is actually the reaction rate. So it will be like this. So this is very important for us. We have to know the CVD process that you are handling, depending on the temperature at which you are wanting to operate it, and there are various reasons why you may choose that temperature. Maybe the reaction takes place at an appropriate rate at that time, so that you cannot wait for hours, for example, to get a very small thin film, right? So those may be the considerations, or maybe purity of the films and so on. A lot of factors can be there. So you have two regimes, and you will have an intermediate regime where it transitions from one to the other. Now it turns out, based on this, realizing whether you are in the reaction rate limited region or the mass transport limited region, you can actually decide how you want to design your chamber. You know what to expect. Okay, and you can make sure that you do the right things to get the appropriate results you want. Usually, here is a couple of examples. LPCVD, it's a low pressure system. Diffusions are very much comfortably can reach the region, although the pressure is low, but because there are no scattering and all that, usually the reacting species can diffuse very fast to the location of reaction. And although the temperature is high, the limit is actually the reaction rate. So LPCVD around 1 torr is actually reaction limited process. On the other hand, atmospheric pressure chemical vapor deposition at 400 degrees centigrade is actually mass transport limited reaction. So according to that, you have to design it. So let's see what we need to do and what are the factors that will be there. We'll see next. So I have given the comparison of two regimes of operation. So left side is mass transport limited regime, right side is reaction rate limited regime. So let's go point by point. Mass transport reactant regime, as we saw, occurs at high temperatures. Because reaction rate is very high, the limiting factor is mass transport. Reaction rate, on the other hand, occurs at lower temperatures. because the reaction rate is so low, enough material is coming but not able to react because the reaction rate is low. So, this is what is the first point. The reaction rate exceeds the rate of arrival of reactant species, in this case mass transport. So, that is why it is limited by the arrival of species. On the other hand, sufficient reactants are readily available, but they are not reacting because the reaction rate is not proceeding that fast. So, that is a difference. In the mass transport limited regime, deposition rate has a weak dependence on temperature. Why? Remember that diffusion rate has a weaker dependence on temperature, and the limiting factor is diffusion rate. Even if you make the reaction rate faster, it is not going to benefit you much. You need material to come in faster. So, you have a weaker dependence here. On the other hand, in reaction rate limited regime, if you increase the temperature a little bit, exponentially your reaction rate will go up. So, it is very strongly dependent on temperature. So, what does it mean? When you are using reaction limited regime, you better have very good control of temperature across the various wafers, parts of the wafer, because the reaction is going to be dependent on the rate of at the temperature. So, if it is dependent on the rate of temperature, if one place is slightly cooler than the other, it will have lesser reaction. That means the thickness of the film will be non-uniform. On the other hand, the temperature has weak dependence, so temperature is not that critical. So, it is less critical. It is critical in the sense that does not mean you can make a huge variation in temperature, but we are talking of small variations of say 1%, 2% variation in the wafer. That will make a big difference, bigger difference in the reaction rate limited compared to mass transport regime. So, temperature is less critical for this, it is more critical for this. Temperature uniformity is very critical on the wafer. On the other hand, we need to ensure in mass transport regime that the gases that are coming, reacting gases that are coming, are piped in correctly and they are reaching all part of the furnace and all part of the wafer where the reaction has to take place. It should not be that at the inlet part of it, lot of gases are available, and so more reaction takes place there, and then very little is left for the tail end of it near the exhaust. So, you find that the thickness is more in the initial part than where the exhaust is taking place. So, this is a challenge. So, you have to design your chamber here when it is mass transport limited such that the species can reach all parts of the wafer. On the other hand, in the reaction limited regime, since the rate is very slow, there is a lot of accumulation of the species around. So, it does not matter if there is small variation, but again, as I said, you would want to, you will do well not to make sure that there is huge variation, because it may happen that it ends up reacting and then you will have non-uniformity. But what I am saying is less critical. The higher priority should be for temperature in the reaction regime, limited regime. Higher priority should be for the how the gases are spread out for reaction over the wafer. So, examples: atmospheric pressure, CVD, SiO2 deposition, as I mentioned earlier. So, what you find here is you make sure you horizontally stack it. If you vertically stack it, the gases that are coming from the side has to go inside the wafer. We will see pictures shortly. So, you do not want that. You want to make it flat so that the gases, as they are flowing, there is a greater chance of uniformity of material available. So, that is why you tend to have more horizontally stacked wafers for in the case of mass transport limited regime. On the other hand, if it is temperature limited or rate limited, there is a lot of accumulation of the reactant gases. So, you can actually pack the wafers much more compact manner. So, there is a trade off. So, the throughput will be higher in one case because you are able to pack a lot more wafers, and in one go you are able to process a lot of wafers. So, this is a design problem and you have to make sure, but these are points to remember. So, let us conclude the first section of our discussion on CVD. What are the takeaways? A variety of CVD system exists, and in fact many more are there. I might not have mentioned some of them, and also many more are likely to keep evolving, because the whole idea is what I discussed about CVD process. So, there are a variety of them. What is beautiful about this CVD process is you are likely to get high purity films with the desired chemical composition. After all, it is a chemical reaction, and the economy of the process is very attractive. It's a low cost process many times. Of course, it becomes sophisticated and sophisticated and the cost goes up, but the base process is economical and scalable. Now, formation of CVD film, this is the key part that I want you to take away from this discussion, and because these are the concept points. Technology, when newer and newer ones will come, but if the concepts are in place, whichever technology comes, you will be able to grapple with it. So, what are the steps in CVD? There are 5 steps. The gases come in, you have to bring them closer to the substrate. At the substrate, they absorb, they react, the byproducts go out and they get flushed out, and then slowly the thin film grows. So, what you prefer in this case, chemical reaction should be close to the substrate, and that is what we call as heterogeneous reaction. It was discussed in this in some detail earlier. Then there are 2 regimes of operation that we find, because the mass transport that happens in the gas phase and then the reaction that happens close to the substrate, if it is a heterogeneous reaction or wherever it happens, so there are two aspects of it. So, based on the temperature dependence, usually the mass transport is weaker dependence on temperature, the rate reaction is a Arrhenius relationship. So, there are 2 regimes of operation. Mass transport limited regime, it depends on the incoming reactants. Okay. So, this happens at higher temperatures for a particular reaction, and reaction rate limited regime, this happens for a particular reaction and process, it happens at the lower temperatures. So, you have to make sure you design your, and depending on which one you choose, there may be many parameters because of which you will choose a low temperature or high temperature. Ideally, you want to be in a flat region because some variation will be forgiving, but you cannot predict all that. So, first order, you want to design, you have to consider all the factors and decide where you are going to operate, and depending on where you are operating, you design your chamber and the process. If it is mass transport limited, you want to make sure the gas species are available all through, and the removal of the byproducts is also happening smoothly all through. On the other hand, if it is rate limited, you want to make sure all parts of the wafer are at approximately preferably the same temperature, as close to each other as possible and uniform. That is the whole purpose of knowing the process. Okay, now that we have seen the very basics of CVD, what it is all about, let us quickly look at the CVD systems. I won't be going through all the CVD systems that may be there, but try to highlight some key points about a CVD system, and also look at some cursory look at least of some of the popular CVD systems. Again, I have taken a lot of the ideas from chapter 6 of Wolf and Tauber, which was written by Andrew Coulson and Richard Tauber. So, what will be the outline for this? It's as follows. I would like to give again a broad overview of a CVD system. There are various types of CVD systems that are there, but there are certain things you can always figure out, right? There are various types of living organisms available, right? But you always know what is a head, what is a body, what are the limbs for most of the creatures, right? So, similarly, CVD system also has a form to it. So, let us see what that is. Then the categorization of CVD systems, some of them we will look at it, and some of the CVDs and some just highlight some of them, although I will not go into too much detail in that, because it is good to be aware of some of this, and there are many more, and I will welcome you to do research and learn more. So, what is a basic CVD system? So, basically the good thing about CVD typically is it is an open flow system where gases flow into reaction chamber and byproducts flow out. Usually this is the nice part about it. There will be bells and whistles and some sophistication coming in for various types of systems, but at the bare basics, it is an open flow system where gases are continuously coming in, they are reacting and then they are going out. All of them typically will have diluent gases. They will all have diluent gases, typically use hydrogen, depending on what you are using, hydrogen, nitrogen and argon. And you want to make sure that diluent gases don't react, but they create the partial pressures that are needed, which are favorable for the reaction. So they bring the reactants to the place of reaction. They facilitate in bringing the reaction phase of reaction without interfering in it, hopefully, and they also help in removing the byproducts. So, and for pumping the system and things like that, it may be helpful many times. Also, diluent gases are, help in making sure that if there are corrosive gases and all, it protects the whole chamber, because beyond a certain level of concentration, it may be harmful for the system, right? Now, since we may be using corrosive gases or explosive gases, when you are exhausting them, or even as a byproduct if something is forming, you have to make sure whatever is dangerous or corrosive, it goes through what is known as a scrubber. That is a technical word they use for it. It goes through a system where the dangerous gases are made harmless. Okay, and depending on the gas, you take whatever action that is needed. The chemists will know what to do, and you have to implement it appropriately. Whichever is not harmful, say it's just hot nitrogen gas that is coming out, then you can just let it into the air, or CO2 coming. Of course, large volumes of CO2 and all, you have to be careful, but typically whichever is benign and will not hurt, you can release it to the atmosphere or wherever is whatever is the rule in the lab. So here I have shown as a example, and even Wolfenthaler also borrowed the idea from them. They have shown the PECVD chamber schematic here. So you can see open flow system. So all these gases are coming in. There is a reaction chamber, and then they all get exhausted out. In the case of PECVD, there is a vacuum is needed in order to strike the plasma, and you have an additional RF plasma that is linked. According to what you have, various LPCVD will not require this RF, but on the other hand, LPCVD will require a vacuum pump. Atmospheric pressure chemical deposition will not even need a vacuum pump, because it's at atmospheric pressure, right? Sometimes you operate below atmospheric pressure, sometimes you operate slightly above, but usually there is a positive pressure of the gases that are coming in, and they push things out through the vent. So and then you can see there are lots of diluent gases also that are added. Silane and all is there, which is not very good to have without protection. So, but then that's why the diluent gas is coming, and you design it properly. So I hope you get an idea of what the thing is. It's a very simple system, open flow system, where gases come in, reaction chamber, and it goes out. The whole game is to make sure that this flow of gases is very well controlled, and this is where VLSI processing has been so successful. We are able to control the flow of gases very precisely and over a wide range of flow rates. Not just that, when the gases come in, how do they interact with the wafers? Are they able to reach all parts of the wafer? How are the wafers placed within the chamber so that they are all at similar temperatures or same temperature ideally? And are we making sure that the byproduct gases are able to be pumped out conveniently? So these are some basic things that is true with all the chemical vapor deposition systems. So if you look at it, whatever I said, I put it here. The various components that you may have to deal with when you are talking of CVD are: you need gas sources, you need gas feed lines. So there are people who are experts in building all these feed lines, which are without leak, which ensure that there is no contamination coming in, and so on. And then this is an important thing, mass flow controller, which controls the flow, and we can do it very precisely, and that makes a big difference. And then of course the reaction chamber, the design of it is very critical. Then the substrate heating and energizing. During the reaction, you may want it at a higher temperature, or you may want it flooded by a certain wavelength of light, or you may want some plasma around that so that the reaction can take place at a lower temperature. And of course, it will require a lot of thermal sensors, temperature sensors, and what many times you use it as a feedback, because you know what is the if you find that there is a variation, you can at least address it. Okay, and so there are lots of feedback systems in this, both with the flow rate as well as with the temperature, and it ensures that you are able to get the right thickness of the thin film. If you find that the rate is going very fast, rate of growth is very fast, you slow it down. So there are other sensors as well. There are lots of sensors. Primarily, there are two things that you have to which are distinct in this. Not that it may not be used in other places, but typically you're likely to find in CVD a mass flow controller and a reaction chamber. Okay, so now some of these systems will need in the reactor pumping systems, LPCVD, PCVD, which we are familiar with, and many others. Ultra high vacuum chemical vapor deposition, for example, obviously will need a lot of pumps, and we discussed about those little earlier. And then the heat, the energizing part, many times, very often it is just ohmic heating. Okay, you pass electric current and make sure that the substrate holder is heated, or it's cooled. You want to keep it at a particular temperature, and during the reaction the temperature is going up, you want to maintain it, you can do that. So you have to have cooling systems, and many times it can be RF which is providing the energy for the reaction, and sometimes photons, maybe various other ideas also people will come up with. Now we saw that one of the key components that was distinct was the mass flow controller. Mass flow controller is essentially telling you what is the gas flow rate through the pipe. So how does it work? You have this mass flow controller, there is inlet here, the incoming pipe, the one side of the pipe is here, and the pipe that goes to the chamber or goes out wherever, you can place it wherever, is here. So the gas comes in and goes through like that. Okay, so it has a valve. This valve, as you can see, the gas comes in like this and goes like that. So this valve can be open or closed by electromagnetic servo valve. Okay, you can do that. Now you need to find out how much is flowing, and this can be done with the feedback, and this is where the feedback comes in. The gas is flowing, you sample it and make sure that you know whether it is flowing appropriately, more or less. If it is more, you close the valve a little. If it is flowing less, you open the valve a little. So you have to do that. How do you do that? As you can see, there is a sampling path here. The gas comes in through this and goes back and rejoins with that. But in the process, in between here, one of the popular methods by which the flow rate is determined is the thermal type. There is also a differential pressure where you find the pressure here, and then you can do analysis, but that is not as popular as a thermal type of sensor. The reason is it is very robust. Okay, and so how does it work? It actually is very fast in the way it operates as well. So gas is sensed, it goes through. Based on what is done here, there is a heater here, essentially it heats it up, and then by sensing the difference in temperature, you are able to find out how much flow is taking place. So typically the unit of flow that is used is standard cubic centimeter per minute. This is a commercial unit, it is not an SI unit. So standard cubic centimeter per minute means standard refers to here a standard temperature and pressure, 273 Kelvin, 1 atmosphere. Okay, so what would be the thing you find out? That is equivalent to 1 by 22,414 moles per minute. So because Avogadro's equal volumes of gases have equal number of molecules in them, and we know an Avogadro number will be 22.414 liter, right? So that is where this comes in. So essentially you can even talk in terms of moles per minute, what 1 SCCM is. Now the sensor tube that we talked about, we have a sensor here, there is a heater present here. and there are two temperature sensors. One temperature sensor is before the gas enters the heating part of the sensor, sensing tube, and one sensor on the other side. So you can measure the temperature difference between the two sides, and we can say that the mass flow that is there, it can be modeled this way. The mass transport or mass flow that is happening will be kappa times W sub H. W sub H is the amount of power that is given to the heater and how much it is heating up the gas, and delta T is the observed temperature, and the whole thing to the power 1.25. Now it is clear that all the physics of it and what type of gas is present, all that is hidden in the constant kappa. So, kappa is a constant that depends on the specific heat of the gas density, and the thermal conductivity of the gas. So, it varies from gas to gas. So, usually you have to calibrate this thing. You calibrate it for a particular gas system that you are going to use, and you can always multiply by a product depending on the molecular weight, and sometimes you will have to have other things depend on the other properties of the gas. Now the sensor delta T reading is converted clearly, and these thermocouples may be used in the two ends. So delta T can be used as a voltage value, and once the voltage value is come, you can use it for feedback control. Usually it is given to Wheatstone bridge. So the voltage that is developed across the Wheatstone bridge, that will be telling you how much it is getting heated, and depending on your setting, you can use that voltage to actuate this valve, okay, electromagnetic servo valve, and that way you can actually control, have a feedback control on how this happens. Now this feedback control can open and close the valve, yes, but initially as you just start off, the heater may not be fully operational. So you will have to wait for some time, and there can be a slight overshoot of flow initially. Initially there will be a lot more flow, and then it will come to the feedback control and it will be correct. So you have to watch out for that, and depending on what you are doing, so you have to create protection for that. So this mass flow control is an excellent tool, instrument, and this is easily available, and of course you have to handle it properly. You have to make sure that there is no leakage, because if corrosive gases are going through, you don't want it to leak through the mass flow controller, and as a result causing danger to the people using it in the lab where it is operational. So these are things that you have to watch out, and there are companies which are able to make robust mass flow controllers. So we need to calibrate this mass flow controller regularly though, and if your gas is changing also, you have to calibrate it, or you should know there should be a table by which you are able to calibrate, and you do this, make the setting accordingly, or you send it to the company and get it calibrated and bring it back. So that was about the mass flow controller and how the gas flows through it. Now let's quickly look at the CVD reactor design for the various types. I'll just give examples, pick some pictures that I took from book and other sources. So they may be classified, the designer can be classified on various criteria. As we already saw, pressure of operation, atmospheric pressure, low pressure we have been talking. So this is one of the popular ways in which you divide the reactors. So either it's an atmospheric pressure reactor or it's a low pressure reactor. Then the other way in which you classify after that classification is, what is the source of energy for the reaction? If the reaction source is thermal heating, you design it in a particular way. Will the walls of the chamber get heated in the process, or will only the substrate be heated and the walls will be at room temperature? You would prefer the walls to be at room temperature. Why? You don't want the reactions to take place in the wall, but sometimes it will take place. So that means you will have to clean it. LPCVD system, for example, very often you will have to, the typical design, you will find that the walls will be hot wall furnace, right? So that way it will form, the reactions will take place, deposits will have formed on the walls as well. So periodically you have to clean it, and also it may cause particulates. So those issues are also there. So hot wall you want to avoid, but it's a simpler design. Cold wall plasma is also possible, and very often it's more attractive for plasma enhanced chemical vapor deposition, a photon induced chemical vapor deposition. So, as CVD system as discussed, atmospheric and low pressure, and then within the atmospheric you have hot wall and cold wall, various categories. And in the atmospheric you have continuous motion and epitaxial, continuous motion of plenum and nozzle, and epitaxial you have barrel and pancake. Okay. Low pressure you have hot wall, plasma enhanced, and vertical flow isothermal. Then plasma you have hot wall, cold wall, and cold wall planar single wafer. So these are some of the categories. We will look at some of these examples. Plasma enhanced vertical, we have already seen a little bit, we will see a little bit more some of these. Then vertical flow isothermal, I will try to show this barrel pancake, just a glimpse of what it is. So atmospheric pressure chemical vapor deposition, how would a chamber look like? When they started off, one of the popular methods was to use a horizontal tube, and notice the wafers are lying flat because the reaction is to take place on the surface of the wafer, right? And then when the gas comes in, it goes through, and you want to make sure that the last wafer gets adequate amount of reactants for the reaction to take place at the same rate. If it is going to be limited by the species that are coming in, then you are in trouble. So one of the ways, of course, is to make it into rate limited. That's one of the ways in which you could handle it. But then another thing is to design it such that the last one will have sufficient reactants, because the ones that are above this are unlikely to react with the first wafer. So they are likely to travel all the way, and you will have enough material there. So this is a simple horizontal tube design. Then you have a gas injection type. So here what you are trying to do is, you have a conveyor belt, a moving belt where the wafers are coming, and you have all the reacting gases and as well as diluent gases. You bring them, and with the help of proper design, introduce them right next to the wafer where the reaction is take place, and the wafer will be at the appropriate temperature. There are more better designs for how the gases are handled and brought to the place. So you have a plenum here. So you will have reacting gas that are coming in, and it's in this chamber it spreads out, and then uniformly it comes in to the wafer, so that the full wafer will see a very similar situation. That's the key thing. So let's see what is special about APCVD. Clearly, it's a simpler structure. You don't need any vacuum pump or anything. You just need a metal chamber or a chamber with the proper coating, so that there is no contamination. Its appropriate mass flow is important. So you need mass flow controllers, of course, but you should design it such that the gases are reaching the place where the reaction is taking place. The temperature is not the limiting step. Very often it is the gas reaching the point that is the limiting step. One challenge you might have, or maybe you have to live with it and you have to know how to use it, gas phase reactions are very much possible, because you are bringing, for example, in the first case, all the gases are coming in and they are all together most of the time. So there is a chance that they will react. And of course, you try to keep them as much separate as possible and release them only close to the substrate of the wafer, here and here. But all the same, many times they do interact, and you can have gas phase reaction. Okay, so that's a little bit of a drawback. So poor step coverage can happen, because the reaction is not taking place at the surface, right? So it's depositing from above. So that can end up having gaps. If there is a step, maybe there is a small gap. The gaps are very dangerous, because some gases can remain there, and high temperature, low temperature, the gas expands and contracts, and it may crack the film that is on top of it. So it's not a good idea. Or contaminants, it may be a Gettering site where all sorts of undesirable metals and other impurities may end up getting accumulated, and that may affect your device. So it's not a good idea, but all the same, for many applications it may not matter. Wherever it doesn't matter, you can use it, because it's a simpler structure and low cost. Poor step coverage, and low temperature oxides is one of the places where you can use this. Now from atmospheric pressure chemical vapor deposition, let's go to LPCVD, low pressure chemical vapor deposition. Here it is actually reaction, you design it, you operate it at a point. For that particular reaction it is reaction rate limited, correct. So what does it mean? You can afford to stack a lot of wafers, and because it's reaction limited, you have lots of reactant species moving all around that, okay. And the whole furnace is heated, as you can see the full furnace is, it's a hot wall furnace in this particular case, and then the gases are coming from this side and going this way. And you could have also distributed feeder. While it is true that it is reaction limited, there can be a local depletion of reactants, so you may find that there is a variation. So you want to avoid that, you want to prevent that. So one of the ways is to go for a distributed feed reactor. You can see, instead of sending it from one side of it, you send it everywhere. So even the last wafer will have as many reactants around it as the first wafer. So let's look at it. So it operates in the reaction rate limited regime, and one of the good things is we can control temperature quite well, okay. That's one of the marvels of a modern technology. And we have feedback control and so on. You have to have right sensors, and you should be able to measure it. Sometimes you may have optical sensors to check the temperature. In low pressure, reactants diffuse faster, and that is why we are able to make it reaction rate limited, although the pressure is low and the temperature is usually higher compared to the atmospheric pressure chemical vapor deposition. It operates in medium vacuum, 30 to 250 Pascal or 0.25 to 2 torr. Higher temperatures of 550 degrees centigrade for silicon and 800 to 850 degrees centigrade for nitride oxynitride is what is typically used. We'll touch upon this in the next lecture briefly. Many types of films are formed. Polysilicon popular, you can make it undoped and so on. Silicon nitride, silicon oxide, phosphosilicate gas, you can have doped SiO2, borophosphosilicate glass. They are advantage because they flow nicely. We have talked about these when we talked of process integration. And then you can also have tungsten deposition, LPCVD. You can see the versatility of such systems. You can vary the temperature to compensate for depletion of reactant gases along the tube. Because it is temperature rate limited, you can actually tune the rate. So although it's rate limited, the concentrations may be different, and because of the variation in concentration, you may get a slight different rate formation. So since you can control the temperature, the place where you are likely to have more depletion, so the later part of the furnace where the gas is coming from one end, you could actually raise the temperature a little bit so that the reaction rate will be faster. Of course, it will hold up to a point. If it is completely depleted, there will be nothing for it to react with, right? So that will not work, but you can tune it better, and you can actually do design of experiments and so on to ensure that there is uniformity across the wafers, all the wafers, and on the wafer also in different parts of the wafer, in the center as well as the periphery. Another trick, of course, is to use distributed feed of gases, as we saw here. Now, for distributed feed of gases, we have horizontal tube reactors, like we have that is shown here. You can also have vertical flow isotherm reactors. Isotherm means same temperature everywhere, but vertical flow, and that ensures the distribution of gases are similar everywhere. So this local depletion to make a slight change in the reaction will be less. So this is the image of a schematic and a photograph of a vertical isotherm LPCVD reactor. So the gas is coming through this small pipe, going there, and then it's coming out, and then you have the heaters. So you have these, this is all vertical. One advantage of this thing is, because it is vertical, you will not have any dust settling on it. Horizontal means there will be dust settling. That's where atmospheric pressure chemical vapor deposition, there is a challenge. You make it flat, right? So whenever there is some dust particle comes in, it can settle there. If it's vertical, There also dust particles could stick to the wall, but its chances is less because it may go right through. So this is a isotherm LPCVD reactor. So there are various varieties and people come up with newer designs. Now let's look at PECVD. We also already saw the overall schematic of the PECVD. Gas coming in, where the reaction takes place, how it exhausts, and there is an RF system that creates a plasma inside. Now how does it create plasma? Here I am trying to show that with the help of these images that are taken from Wolf and Tauber. You have graphite boards, and on that you have graphite electrodes, because you are, remember, it's RF, and then the substrates are placed on them. So you can see the graphite and how many you are able to pack a lot of them next to each other, and they are kept such that you are able to have a lot of them reacting, and the plasma ionized chemical vapor reaction happening simultaneously on many wafers. So throughputs can be high, and also it can be quite conformal. So this was invented in early 1970s with RF plasma, and it operates 0.1 to 5 torr. Okay, not very high vacuum, but it does, you need vacuum. And typically the temperatures are 400 degrees centigrade, and this is remarkable because you can do depositions on top of metals. Metals will not melt. Okay, so at 400, many of the metals, depends on the metal, but typically the metals we use, copper and all that, you can actually have a PECVD deposition happening, and also the thermal budget is low because you have lots of devices sitting underneath, right? When you are doing the metal line deposition and oxide insulator depositions on the top. So when you are doing the oxide deposition, you don't want the temperature budget, thermal budget, to end up affecting the profile of the devices that you have made underneath. So as I mentioned, 1970 it is invented. RF plasma 450 to 13.5 megahertz, 0.5 to 1 to 5 torr, 400 degrees centigrade. Glow discharge is what is transferring the energy. Essentially, the excited electrons that are present in the plasma end up energizing the reacting molecules, and they end up reacting at a lower temperature. Silicon nitride over metals, as I mentioned, is one of the really remarkable things that PECVD is able to do, which allows us to keep processing it even after the full device is made without worrying about too much of distortion of the profiles that are formed underneath, and also the metal not being affected. So we need to balance plasma density and gas flow, and those are the parameters: plasma potential, plasma density, gas flow rate, and there are levers that are, and the power that you put in with the RF. So these are usual levers that you use for controlling the plasma's property and hence the reaction properties of the reacting gases. One of the challenge with this though is growth rate is faster also. So very often you find this not stoichiometric, and not just that, there's incorporation of products, that the byproducts that are there into the thing, especially hydrogen. Hydrogen gets some, you can use it sometimes, but many times it can also be a bother because hydrogen moves. When you go to high temperature, hydrogen may move and change the property of the device, which is earlier satiated by the hydrogen that was present. So that's one of the challenges. So stoichiometry and incorporation of byproducts is the big challenge. Okay, and so here there is a photograph of a system. So what I am going to do now is I am going to compare the three popular CVD systems. These are the three: atmospheric pressure chemical vapor deposition, LPCVD, and PECVD. So let's see what are the advantages and disadvantages and application. APCVD, as we saw, is a very simple reactor. Atmospheric pressure, you can have very fast depositions because it's just a chemical reaction, and you are taking it to high temperature. You have the gases, increase the gas flow rate, you have higher rates of deposition, and at lower temperatures typically you don't operate at very high temperatures. What is the disadvantage? Very poor step coverage, and also particle contamination, especially if you are laying it flat, because if some particle comes in, it will get stuck there. So it's not that becomes a disadvantage. But where do you use it? Whenever you want low temperature oxide and you are not too much worried about step coverage and stuff like that, and both doped and undoped can be achieved with APCVD. LPCVD on the other hand is very sophisticated. You get excellent purity and uniformity. And not just that, since it is it is reaction rate limited, excellent step coverage is achieved. Okay, and a large wafer capacity, because you are able to pack a lot of wafers and you are able to get a lot of wafers processed simultaneously. So its capacity is huge. But what is the disadvantage? The temperatures are high, 1000 degrees or so. That means that the doping that you have already put in, they can shift around. So you have to build that in your thermal budget for that particular profile. So that's one of the challenge. And the other thing is, because its excellent purity and conformality is there, the deposition rates are slow. And that's a usual trade-off. Okay, if you have good quality stuff, you better give time for getting it done. And that's what you find in LPCVD. But that being said, it has a lot of important places in VLSI where it is used, and you build in the thermal budget. You design it such that in spite of the high temperature process, your device profiles will not get affected. Where do you use it? High temperature oxides, both doped and undoped, silicon nitride, polysilicon, tungsten, and tungsten silicide. Silicides also it can be used. So this is a nice it's a very robust system. The challenge is you need vacuum and you need to operate at high temperature. PECVD. PECVD advantages, whatever typically you find in plasma process: lower temperature, fast deposition. Okay, so you can throughput is high, good step coverage is okay. But what is the challenge? The chemical and particle contamination is there. What are the application? Low temperature insulators over metals, as we saw when we want to make nitrides on top of metals in the back end of the line. Passivations, it can be useful. Passivating layers, that is, nitride is one of the passivating layers. So PECVD can come in handy. Okay. So there are three popular ones. Having seen those three popular ones, let's look at some of the ones that are also becoming important and are important in their own right, in their own niche areas. I'll talk of a couple of CVDs. One is epitaxial CVD deposition equipment. There are two popular reactors for this. One is induction heated vertical pancake reactor. It is just the very the way it looks, that's what gives it name, vertical pancake. And the other one is radiantly heated barrel reactor. So you have a heater which is radiantly heating the wafers that are there on this susceptor that you can see at the center. Here the susceptor is here. So these are the two popular ones that are used for epitaxial chemical vapor deposition. The RF inductively heated horizontal reactor also exists, and there are many others, but then these are the two popular ones. The temperature is monitored by IR sensitive optical pyrometer focused on the wafer. So you can check and see, and then you can use it for feedback if required. You can also use thermocouples in the barrel reactor. Thermocouples may also be used, and that is useful for ensuring that you are keeping track of the temperature, the uniformity, and you can control the process rates and so on. So quickly, some points about pancake reactor. Typically, the wafer is in silicon carbide coated RF heated graphite susceptors. So RF is what is heating these things, and they are actually graphite susceptors, but they are coated with silicon carbide. Gases are distributed symmetrically. As you can see, it's going from the center, and there is certainly circular symmetry, and if you turn it around also, even better. Now, the gases distributed symmetry operates at 100 to 200 torr or at atmospheric pressure. So that's a good thing, and just below atmosphere or at atmospheric pressure, right? 760 torr is 1 atmosphere. What about barrel reactor? This susceptor that you have, it's a hexagonal shape and again silicon carbide coated graphite. Now the gases come from the top and are exhausted at the bottom. They come from there and they go this way. And also it's water cooled quartz lamp are used for heating. It's radiatively heated with the quartz lamp. So that means contaminations are less, more efficient. You can control it, you can turn it on and off. All those issues are feedback controls and all that. Because of this very design, it is less susceptible to particles, and that's very important when you are growing things epitaxially. Okay, and epitaxial growth is becoming increasingly important in some of the latest devices, because many times you grow epitaxial silicon in order to get more areas, especially in the contacts of the source drain, as we saw earlier. Let me also talk about another important CVD reactor. I think it's become very important in the modern times. Atomic layer deposition, and it has a lot of excellent features in it. Okay, so essentially the process steps are divided into pulses. So pulse 1, you will have some gases coming in and they react with the full surface, and you give it time to make sure it reacts and you send in adequate amount of the reactants, and they form the monolayer film on that. Okay, once that is done, and you of course you make sure that by experiment you know when the full surface would have reacted, and these are possible by help of physics and chemistry. And then what you do, you purge the whole thing. Whatever was originally sent, you remove everything, and the byproducts also you remove. So the chamber is now in pristine condition, or almost pristine condition, or similar to pristine condition. Then what you do, the second layer that you want to deposit, it could be the same thing, but it could be also something else. You introduce the second layer that is coming in. Okay, the second reactants are introduced, and then same thing happens. A layer is formed, and then you pulse it with the next pulses. You purge the whole thing, and again bring it back to the thing. So you have two layers formed here. And actually it's a play with chemistry. The surface is such that it will react and form a monolayer. So you are able to control the way in which you are doing. So atomic layer after atomic layer, you are able to do this. And this has become very popular, and this can be repeated ad infinitum, right? You can keep on doing it to get the amount of thickness you want. Of course, the challenge will be the time that is required. So now what they do is they have multiple steps like that in sequence. So you may have maybe 5 to 10 sequential stages. So in one shot, you are having 5 layers grown. So and considering the nano layers that we are requiring nowadays, this is very attractive. So what are the key aspects of ALD? And this is where the uniqueness comes in. It's a self-limiting process, because it's by chemistry you make sure only one monolayer is formed. Once the monolayer is formed, the second layer will not form. So that's one thing. So one precursor at a time you are doing it, and self-limiting process. And actually you can use the chemistry to even if it's the same thing grown again and again, you can use chemistry to make sure only one layer is formed, blocked, then you have the second layer formed, blocked, and so on. The cycle structure with deposition and purge layer avoids any gas phase reaction. So it is heterogeneous reaction, right? It's coming and reacting only at the surface. No other reaction is taking place anywhere else. Semiconductor manufacturing of high K and metal gates, high K metal gates and capacitors in nanotechnology, etc. It's a very popular system. Actually, it's a very popular system. The limitation, of course, is the speed, but it's a very popular if you are wanting only a nanometer size layers, and very predictable. You can deposit oxides, nitrides, sulfides, metals, etc. It can operate at room temperature as well as 800 degrees, up to 800 degrees, but typically it's slightly above room temperature, 100 degrees to 200 degrees, not slightly above boiling water, of course, 100 to 200 degrees centigrade you operate it, and that opens up a window for many reactions. The advantage, of course, exceptional conformality. It's conformal in the sense follow the contour of the surface very well, because only the monolayer on the top is reacting, nothing else. good coverage of high aspect ratio structures. If you have a trench and things like that and you want to deposit, it's wonderful. Precise thickness control. Why? Because it totally is dependent on the number of cycles. Only one monolayer is formed in a cycle, so number of cycles tells you how many monolayers you have. So excellent thickness control. Film is dense, uniform, and of very high quality. It allows for deposition of various materials, and also in the modern 3D electronics that we are coming up with, this is playing a very important role. It can be very good for an encapsulation layer and many other things. Okay, so ALD is a very popular. CVD is becoming popular in the labs, and certainly in manufacturing it is popular in its own right. Okay, so now let's come to the final takeaways of the CVD system. Control of flow rate and reactor designs are often distinct in CVD system. These are the two parts that are particularly different. How to control the flow rate and the reactor chamber, because you want to bring in the gases and make them react right next to the surface. That's why ALD is unique, because you are making, the way it is done is the chamber has to be designed to have those monolayer formation, right? So the control and flow rate, which is mass flow controller, and the reactor design, that's what is especially distinct about CVD. Other aspects of gas lines and things like that you may find in many other systems, and there is a lot of commonality there. The classification of CVD is typically based on pressure of operation, high pressure, low pressure, or atmospheric pressure and low pressure. Then also the energy that is used for activating the chemical reaction. It can be thermal, it can be plasma, photon, and maybe in future many other things that may come up. Atmospheric pressure chemical vapor discharge system is simple but is limited by the quality of films typically. LPCVD needs higher temperatures but very good quality of films. Chamber is a little bit more complicated than APCVD, but that's not something we complain too much about, because those technologies are so robust now that yeah, it is something that you need, but it can handle them. PECVD allows for low temperature film deposition, but again quality can be suspect in some situations, some applications, depending on the application. All this you have to choose according to what is needed for your application. For CVD, for epitaxy, vertical pancake and barrel reactors, they are popular. ALD is becoming increasingly important method for forming good quality thin films, especially atomic layer films. Many other CVD system exists. Example, metal organic chemical vapor deposition, I didn't mention it. It plays a very important role. You can get very good quality films at a reasonable temperature. Of course, you have to handle certain gases, metal organic gases, and other things you have to do, but it is a very good system as well. With that, we'll conclude the discussion for this particular lecture. Thank you.